greater than 1, right? And in point of fact, we also know that here's my x-axis, here's my y-axis, we'll say. I'm going to look at this. We know what this is. This is the graph of our exponential function base 2. And since e happens to be greater than 2, we know that the graph of e is going to look something like this. So let me think here. I'm going to probably pass to this point here. So we'll say this point here, this is about 2.71. So we have that the graph is going to look like this. And then here, for negative values of x, it dips below the graph of 2 to the x power. Okay, so this red curve, this is the graph of e to the x, and here I'm comparing it, the graph of 2 to the x. Okay, all right. We also know that because e happens to be greater than 2, we know that if we look at a function h of x equal to e to the minus x, the graph of this is going to look like the following. So this is let me just see something. Did I say what I wanted to say right? Yeah, I did. So this would be right about here, I guess. Be over here. We have that. Oh, wait, one minute. I'm a little bit lost. Yeah, I did that right. I did this wrong. So the graph is going to look like, this is 1, 2, so it would be up here. So it's going to look like this. And then it comes down. And, oops, and it approaches this line exponentially. Okay, and this value here, this is supposed to be, this is 2.71, and right here, this is just 1. Okay, so that's what the graph of h of x equal to e to the minus x would look like. It's just the reflection of the graph of g of x equal to e to the x about the y-axis. So this is something that we've seen before. Well, the reason this exponential function base e, this is actually called the natural, so this is called the natural exponential function. So whenever you see g of x equal to e to the x, you know you're dealing with the natural exponential function. And this is really one of the most important functions in all of mathematics. For instance, it models population growth. So here P, this is no longer principal. This is population size, and it's a function of, we'll say, some time measurement, we'll say years. This is often represented as P sub 0 times e to the RT, where r happens to be a positive number, all right? And p sub 0 is the initial population. So what do I mean by that? I mean, p sub 0 is equal to the population, the size of the population at t equals 0. So this is just going to be p sub 0 times r to the 0 power. E to the 0 power is e to the 0 power is 1. Okay. So that's one of the many things that the exponential the exponential function models. Another thing that happens to be modeled by the exponential function is radioactive decay. So with radioactive decay, you have some radioactive material, and say you have an initial amount of it. We'll say A sub naught. So A sub naught is equal to the number of kilograms of some radioactive material. All right. Then what you find is, so with a radioactive material, what happens is the element, the material, is actually changing to a different element over time. So the initial amount of the material that you have is actually going to decrease with time. And what we find is the amount of material after, let's say, t years. So we'll measure the time in years again. So this is the amount of material after t years have elapsed. This is actually equal to the initial amount of material, A sub naught, times E to the minus R times T power. Okay, so here, the difference between this and population growth, the exponent here was positive for population growth. Now this exponent is going to be negative because here I'm assuming that R is greater than 0, right? So what I have is a function which is decreasing with t. So A of t is a decreasing function of t. Well, there's another model that's very, very important, and this is called the logistics model. And it uses the exponential function too. It's a model of population growth, which looks a little bit different from our simple model that I first presented. And it looks like this. It looks like, we'll say D divided by 1 plus, let's make it K times e to the minus ct, okay? Question. What happens? So what happens to P of t as t gets larger and larger? Another way of writing this question is to ask, what is the limit as t goes to infinity of P of t? So this is equal to the limit as t goes to infinity of d divided by 1 plus k times e to the minus ct. who knows what's going to happen? So what depends on t? Well, it's this term here that depends on t, and as t gets larger and larger, provided c, I'm going to say d, c, and k are all positive numbers. So that's something that I didn't mention that I should have. So d, k, and c are all positive numbers. So what happens to this quantity here as t gets larger and larger? Well, this goes to 0, right? So this limit is just going to be d divided by 1, which is d, right? Now the graph of this, this function p of t looks like this. And this is something that you work out in calculus, but I'm going to show you what it looks like. It looks like this, okay? I should actually do that in red. This is d. This is my t-axis. Initially, down here, we have exponential growth. This looks like the simple population model that we presented initially. But then something happens, things roll off. And we have a point here where we're going from a curve that's cupped upward to one that cups downward. This is concave up from here to here. That's called concave up. And this is called concave down. And this point here is called an inflection point. Now, this logistics model actually models the number of cases of the coronavirus. So we can think of this as the number of cases of the coronavirus. And what we're trying to do, we're trying to hit this inflection point as soon as we possibly can. Okay, so that's the idea. So the more social distancing we do, the closer to this p-axis this inflection point is going to be, which is a good thing, okay? Because not only do we want to hit the inflection point quickly so that this rolls off and it becomes stable, but we want to make d as small as possible. Okay.